Hi everybody. Today we're going to talk about a useful skill for all malware analysts, but one that's surprisingly not that common. That's how to statically find the start of active encode or WinMain in malware. We're going to begin the video with a little bit of background on why you want to do this and how to do it, but then we're going to go into 5 different examples to really demonstrate the topic. That's because for this technique, a picture really is worth 1,000 words. Let's begin with the difference between the address entry point code and WinMain. When you create a program, you write a main function that has either all your code in it or calls all your code. So it's the main function that holds everything you write. You may very well think that when a program gets loaded in memory and starts, it starts at that main function. But that's not really the case. If you think about it, main is a function. That means something needs to call it. The way this is accomplished is the compiler generates library code that places at the address entry point, and that code initializes memory, or allocates memory, initializes variables, does a few more housekeeping tasks, and then finally calls the main function. Once the main function returns, that library code then terminates the process. So that means if you start analyzing your malware at the address entry point, you're analyzing library code, and that's not going to be very helpful. So what you want to do is be able to quickly find the main function so you can analyze active written code and find those malicious indicators. There is one exception to this though. Pack code will generally change the compiler options so that the address entry point code isn't generated, and instead the unpacking sub will be placed there. So for pack code, you do want to start at the address entry point, but that's more of a niche example. It's because the actor changes the compiler options. For the majority of malware, you want to skip that address entry point code and find the WinMain function. So luckily, this is pretty simple to do. That's because most Windows malwares, at least for C, C++, is compiled with Visual Studio's. Because you had the same basic compiler generate the library code, you had the same basic library code to look at. So the compiler generated library code is going to vary a little bit from different versions of Visual Studios to different compiler options, but it'll be roughly the same. That means once you learn the technique of how to look at the Visual Studios compiler code, it'll work across all malware compiled with Visual Studios. And because that's the majority of the Windows malware we're looking at, then that means it's going to help you with the majority of your malware. That does raise a question though. Do you need to start at the main function, or should you start searching for targets of interest, either strings or APIs or things of that nature? So my answer is the way you really should think about static analysis is really source code review. Only instead of doing that source code in C, a higher level language, you're doing it in the low level assembly language, but it's no different. So think about it, if I were to give you the source code and ask you what the code does and to find indicators of compromise, would you start just randomly searching for strings or APIs to see what it does? Or would you take a look at the main function, get an overview of how it works, sort of a table of contents, and use that to decide where to dive down deeper to find those interesting indicators or to determine the capability? If you do that for source code, you should do it for assembly too. A lot of analysts think that it takes longer to do this because you're analyzing code that's not part of the malicious indicators, but that's not really the case, or at least not after you get a little bit of experience. If you think about it, code is really a logical, or written in a logical order. That means if you have a function A, function B, unknown function, and then function D, just by context you can determine that unknown function is C with very little effort. It's because you have that context to help you guide you. You know where you came from, you know where you're going to, you know the surrounding operations, and so that can help you quickly determine that unknown function. If I were just to randomly follow cross-references or indicators and fall into that unknown function, I could spend hours looking at it and might never figure out what it is. So the time you spent up front to determine the general layout of the program and to get the context of where you're going for will greatly pay off later on when you're trying to figure out unknown capabilities and when you're trying to determine where to look at. So even though it is a little bit of upfront cost, it'll give you dramatic time savings over the long run. It does take a little bit of experience to do this, so in the very beginning it could take longer, but if you work at it and gain a little bit of knowledge of how to do this, then it'll save you a dramatic amount of time and you'll really be the way you want to do it. So with that, let's go into the indicators we want for identification. We're really going to be talking about C and C++ files compiled with Visual Studios. They have different compilers like Delphi compilers that will have different library generated code. You have .NET programs that you can go back to the decompiled source code. And so all those are going to be different. But the majority of Windows implants are going to be compiled with the Visual Studios compiler. So that's all we're really going to focus on. but the same process that we use for this will work for the other compilers. If you want to learn how to do Delphi compiled files, all you need to do is learn what the Delphi compiled library code looks like, and then you'll be able to analyze that for basically all of Delphi files to find the main function. So for executables, we're going to be looking for three main indicators. We're looking for location, for arguments, and the return value. When I talk about location, I'm talking about location on the graph view. You don't want to do this in a flat listing view. People are really good at pattern recognition, primarily with pictures. It's how we live our day-to-day life. And so in that graph view, particularly because you had the same compiler code, the target location is going to be in the same rough location on the picture. So once you get used to it, it will literally only take seconds to find it. If you're looking at the flat listing view, you have to try to figure out where all the jumps go to, and it takes a lot more processing time to figure out, and it'll be a lot slower. So the location we're looking for is not the last major code block, but the second to last major code block. That's because the last code block, or at least the big code block, is probably going to call to exit. The second to last major code block is going to be a call to the WinMain, and that's what we're looking for. Next, we're looking for the number of arguments. We're looking for either 3 or 4 arguments. You may be a little bit confused because you may be thinking that main function has 2 arguments, argc and argv, but that's not actually necessarily the case. If we pull up some documentation here, we can see this is the standard C main function in argc ** argv, but Visual Studios, which is what we're primarily talking about, changes that a little bit. It adds this environmental variable. So that means even if you write a main with just int argc argv, Visual Studios will actually add this environmental variable pointers for you. That means the minimum you're looking at is for 3 arguments. On top of that, this is the standard main function that's OS independent. But if you're building this in Visual Studios and using the default template for either C or C++ file, it's going to add a WinMain function instead of main. WinMain is just a Windows specific main function. You can see here we have 4 arguments. In the first argument, this handle the instance is going to be the image base where the program wants to get loaded at. That means it's going to be a large hex value, oftentimes 400,000 hex, but it'll just be some large kind of rounded hex value. So we're looking for in the right location, so the second to last code block or big code block, and they're looking for 3 or 4 arguments. If there's 4 arguments, we want to see the first one with a large hex value, and that will tell us that we're looking for WinMain. The last indicator we're looking for is a little bit more of a minor one, but still useful, and that's a return value. You can see here the standard return value is an integer, gives you the kind of error code, and that return value would be passed to the exit function. You won't always have this, but if you have a function you think is WinMain and the return value gets passed to exit, that gives you your final confidence booster to know for sure you are looking at the main function. So now let's talk about DLLs. DLLs only have 2 main indicators. We're looking for location and for the repeated function. The location is hard to describe, but it's going to be relatively easy to show you an example. So I'm really going to describe this through the graphical example and not go into a big description because there's just no easy way to describe it. The other thing we're looking for is that once you find the location and you have the suspected DLL main, the DLL main will be repeated inside an if statement. So you have it called once, and then you have an if statement and it's called a second time. So that'll give you another confidence boost that you got the right function. A more minor consideration you can look for is if you step into the DLL main and you see the second parameter is compared to a 1, and if it's equal, it goes into what looks like the main function or the active encode, then that gives you another minor confidence boost that you are at DLL main. That second parameter is the attach reason, and the 1 is the DLL process attach. You basically have 4 options. You have process attach, process detach, thread attach, and thread detach. And again, the 1 is process attach, and when you load your program, that's one that's going to get called. And so once that process attaches, you go into the main functionality. The last thing I want to leave you with for the background is really just to practice. If you do this a couple dozen times over a few months, it's really going to become ingrained, and you'll be able to do it within a couple seconds without having to think about it. So the more you practice it, the easier it will become. Particularly when your disassembler recognizes the WinMain function, you should always go back to the address entry point and then walk through the beginning until you find it to see how you find it. That's because a lot of money went into building the disassemblers, and particularly the signature databases. So if it finds it for you, just use the free training. It's the best way to learn something, is use somebody else's money to get the free training. That's really all we need to talk about for the background. All that's left is let's go into the different examples. So all these examples, the hashes are in the description of the video. You can download them from Malware to practice on your own. Alright, so we're gonna go into the graph view, because again we want to do all this in the graph view. We're gonna type G to go, and we go to the entry. The entry is the address entry point. This is where the code's always gonna start. For main functions in or address entry point code in Visual Studios, you're generally gonna have roughly two functions. It's most of the time going to start with a security init cookie that sets up your stack cookie, and then you'll either have a call to a second function or it'll get inline. You see here we have a jump, and this jump, so starting at this address echo F2 Foxtrot, that is basically a second function. In 32-bit code, that's generally going to be inline and it's going to look this way. In 64-bit code, it's generally going to be a separate function, and you'll have to just double click into that second function. Once you get into the second function, whether it's inline or you step into it, then look at the satellite view. So you see at the very bottom here, we have not the red code block, but this last big code block. That's a call to the exit. And if we go to the second big code block right up here, I'm just going to select that. And this function here, 416 Charlie 0, is our call to main. We know it's main and not WinMain because that's 3 arguments. We see 1, 2, 3. And that means we basically have argc, argv, and the environment variables. You see the environment variables comes from this get initial narrow environment. So we have the location, the second to last code block. We have 3 arguments, and then we see this return value goes into ESI, and that's passed over to this call here. It gets cut off a little bit here, so I'm going to expand this out, and we see it's called to exit. So that means we have a function in the right location. We have 3 arguments, and we have the return value passed to exit. That's everything we need to look at to determine its main. So I'll go ahead and hit L to label this and call this main. I'm not going to worry about whether it's main or WinMain. I just generally call it main to be generic. So let me double click this. I'll just show you that the code does look like user code, so you can get that sense of confidence that are accurate. So if I scroll through here, I can see some print statements here. So with build number, so obviously you're not going to have build number print statements inside compiler generated library code. If I scroll through a little bit more, I see I start service control dispatcher, and then I see a usage statement. So obviously usage statements are only going to be the main function, so that should give you your kind of a good feeling that we did indeed find the main function. Let me close this down, and let's go to our second example and see how simple that was. So again, a second example, we're going to open up the graph view. I'm going to type G to go, and go to the entry. And again here, so we see our graph view and the satellite view looks a little bit different. We have the same call to the security init cookie, and then we have our second function is inlined again. So again, I'm looking at the satellite view. I'm not going to this last white code block here. I'm going to the second big one from the bottom. So I select that. I see a function here. I see 4 arguments, and the first argument I see is they're calling image DOS header. It's the 400,000 hex here. It's because the image DOS header is the MZ header, or the image base where it gets loaded at. So this 400,000 is the actual value, and that's the handle the instance. So we had the right location, we have 4 arguments, and we know it's WinMain because the first argument is the image base. We look at the return value, EAX, and this again pushed to what looks like an exit here, and we'll expand that out, and we can see it is an exit. One thing to note here is you notice exit gets the return value, but we see a C exit here isn't passed into the return value. So that's just a little bit different. So when you're looking at return values, if there's a call to exit, you'll see the value passed to it. C exit, you won't see it that way. Sometimes the exit will be buried down inside functions, you won't see it. So that's why it's a little bit more of a minor indicator, but it does give us a good final confidence boost. Let's go ahead and label this 404 alpha 50, hit L to label, and call this main. And again, let me double click one more time just to give you the confidence that we did indeed find active written code. So I'm going to step through the function just a little bit, and I see pretty quickly a call to create thread. And so compiler generated library code rarely is going to have threads inside of it. That's something that actors generally do, or maybe in more complicated functions. That just gives you another, again, a good reason to think that we got into the active written code. Let me close that down. And now we're going to do our third example, and this is the last main example for executables. So I'm going to open up the graph view, type G to go, and I go to the entry. So if you look at this graph view, again, it looks pretty different. You notice all these graph views look a little bit different because of different versions of Visual Studios, different compiler options, but the process using about the same. We see the same call to security init cookie at the beginning, and then the inline function. So I'm going to the very bottom here, so I'm skipping the last couple code blocks and going to that second and last big one right up down here. I see a function, I see 4 arguments here, and then the first argument I see the 400,000 hex again. My return value, EAX, gets into this call, and I'll expand this out to verify that it's exit, and we see it is exit. So those are all our indicators. So I'm just going to go ahead and label this 4294 Foxtrot 0, hit L to label, and call this main. And so you see how quick this is to find the main function. So there's no reason to spend time in this compiler generated library code. You just go straight to it, pretty straightforward. I can't tell you how many times I've seen people follow cross references and oftentimes end up in this library code looking at something that looks like almost malicious anti-debugging, and turns out it's actually just the library code doing exception handling. So being able to recognize this main is a really useful skill, particularly when looking at pack code too, because when you're looking for original entry point, you're looking for basically address to entry point code, and oftentimes this is compiler generated library code. So by being able to recognize this, it just makes you be able to do unpacking that much easier also. So we kind of already showed that the main that we're finding correctly, so I'm going to skip over that now. Let's close this down and go to our next example. So this fourth example is going to be DLL. So I'm going to open the graph view and type G to go, and I'll go to the entry. DLLs, we're only going to do one example because these graphs basically rarely change. Almost, at least if it changes, you can't notice it. So I couldn't find any alternate examples that look different. And so we were basically just doing one example because it'll be the same for virtually every DLL you see that's compiled by Visual Studios. So again, unless the compiler turns off the security init cookie, you're generally going to have this stack cookie set up as the first function inside the if statement, and then you'll call this DL main dispatch after that. So we're going to skip over the security init cookie and go into the DL main dispatch. From here, we're looking for location. So we're going to look on the satellite view. We're going to skip over these first couple small code blocks, and we go to the first major code block here. So you can see this bigger one. This function is DL main. So that's the location we're looking for. The repeated function is it should get repeated in the second big code block inside the if statement, right over here to the right in the satellite view. So if we scroll over, we see it's repeated right there. So I'm going to select it, hit L to label it, and call this DLL main. So if we step into it, let's get our minor indicator of the attach reason. We'll give Ghidra a second to redraw. And if we look at this, so again, we see a call to create thread. So that's more likely to be accurate in code than library code. We see the param2 is compared to 1. If it's equal to 1, that means it's process attached. We go into this create thread. If it's not, we basically close handles or we exit out of here. Actually, close handles just from this create thread. If we right click this one, just so you can see it's the process attached, I'm going to right click it. I'm going to go down to set equate. And when this pops up, I'm just going to search for DLL process attach. We'll give it a second to open up. And the first time you initialize these, they take a little bit of extra time. So I'm just going to type out process attach. We see there's one option, the DLL process attach here. So I can double click that and it should update that. So again, that's a little bit more of a minor indicator to step into it. But as you're learning, that's can be a good way to kind of verify it. Let's close this down. And we're going to do our last example now. This last example is just kind of a bonus example, and it's a little bit more of a niche example. I just want to demonstrate a different type of file instead of the kind of standard file we've been looking at. This is an executable, still compiled with Visual Studios, but it's an AFX C++ file, and so these are going to be a little bit different. I'm going to open up the graph view. I'll type G to go. I go to the entry. So we had the same address to entry point code. So you see the graph looks a little bit different. Because this one's is the AFX C++, we don't actually go to the second code block, we actually go to the bottom. We can see here it combines what's going to be the main function with the exit. So we see locations close to where we're at, but a little bit off. But we see the first argument is a return result of get module handle. Get module handle returns the image base that you're loaded at. So that's the handle of the instance. The push EBX goes with that get module handle. So we have one argument, 2, 3, 4, with the first argument being the handled instance. The return value EX gets pushed to exit. So that means this 407 for alpha 6 is our main function. So I'll hit L to label and call this main. And let's double click here. So now we get into the main function. We see just a call to a library function. It's the AFX WinMain function. Now we could step in this inside of a debugger, and we'll see, I think in the first if statement, there's a call to register plus hex 50 or hex 58. And we can step into that, and that's really the active written main function. But we want to be able to do this statically. I want just to kind of demonstrate that once you learn how to do this, this will be the same for all AFX C++ files you get. So the way we find this, I can close down the graph view. We go to the functions in Ghidra, and I'm going to look for the cwin app constructor. So this will almost always be recognized via your disassembler, at least for Ghidra and IDA-Pro. So we see the tilde at the beginning, that means it's a constructor. So I go to the cwin app here, and I want to go to the first cross-reference. So I see there's only one cross-reference here, and it's listed as function 405 alpha charlie 0. I double-click that, and I'm basically looking for the return value of cwin app. So you can see ECX is the basic constructor object, goes into ESI, and then the return of this ESI goes in EAX. So this constructor at the first address, we put a function pointer table, so virtual function table. So I can double click this, and this is where we're talking about if you go in the debugger, it'd be the reg plus hex 50 or hex 58. I've seen it both ways, so you never know for sure which one it is. So if I put G to go, I'm going to go to this address. I'm going to do 408 5 delta 8 plus, and I'll do hex 50. And we see hex 50 here is just a label, but hex 58 is a function. That means this function, I can hit L the label, and I call this actor main. Because the previous one was main, but that wasn't really what the actor wrote, that was just a C++ call to the AFX C++ main function. Let me go ahead and open this graph view again. And since this was a little bit different, I'm just going to go through and show you that it is active written code. Because you see, this is a little bit hard to tell. We had these enable control container rich edit. So these could be library code, could be actor code. If I go into this function 405 charlie delta 0, and I scroll through here, and this was a wrong function. So I'm going to hit Alt left to get back. Sorry, it was this function right above a new window, so 405 alpha 30. And if we look in here, we're going to see a simple decryption loop. So you can see we're grabbing a byte out of a buffer, we're XORing it, nodding it, XORing it again, and then putting it back into the buffer. So obviously that type of decryption is not going to be in compiler code, so that just gives you that confidence it really is the actor code. So I can close that down. And that was more of the niche example. So again, we're not going too much of how I determined, that was the actor main. It's just to show you that once you learn, in this case, what the AFX address to entry point compiler looks like, or the AFX main function, then you can find it statically, and it'll work on pretty much all AFX C++ files you get at. That's all we need to talk about today. I hope you enjoyed the topic today. If you did, please like the video below and subscribe to my channel to get notified when new videos come out. I also love to know what you think about the video, so leave comments. If you want more reverse engineering tips, follow me on Twitter. And if you're interested in more structured training, check out my website for the malware analysis classes I offer. Until next time, keep on practicing and try to learn something new every day.